Hello, everybody. I hope you're doing well. Welcome back to another video covering Introduction to Machine Learning. So in the previous video, we covered neural networks, logistic regression, and decision trees as our brief intro to survey of models. Another cool model that is worth discussing for classification at least in our Titanium dataset problem, is called the support vector machine. That's what SVM stands for. So there's linear SVMs and kernel SVMs. So think about an SVM as a model that essentially finds the best separating boundary between labels, right? So if we scroll up here, right, to when we've plotted our PCA version of, our train and test, imagine if you can have a model that just somehow can draw a complicated region, right, to isolate, the oranges from the blues. And SVM is doing exactly that, just like you would as a human, right? But there's some mathematics in place that allow for the SVM to do what it does. So this is an example of a linear SVM classifier. And as you might guess, a linear SVM or support vector machine is essentially trying to find what is the best line that separates labels. So in this example, which line do you think is the best to separate the blacks from the whites? Like, without even me telling you, which line do you think is the best intuitively? I'll give you 10 seconds to think about it. Alrighty. Hopefully you guys have thought about it. So let's go through this. So let's look at the green line. So the green line is not really separating the blacks from the whites in the best way, right? Because you see here on this side of the green line, you have blacks and whites in the same spot. So this green line doesn't look good, right? Let's look at the blue line, H2. So the blue line does the job of separating the blacks from the whites, but there's one problem, right? If you take a look at the blue line, right? You see how there are some points right here that are kind of relatively touching it close? This is a problem because imagine if I put a point like right really really close to this blue line. You don't really get a lot of wiggle room, right? For with this blue line of separation, right? You're not really doing a cleanest separation between blacks and the whites, right? With this blue line. But on the other hand, if you look at the red line kind of separates the blacks from the whites. But the difference between the red line versus the blue line is in the red line, you have a lot of wiggle room between the blacks and the whites. So essentially, you're kind of doing a cleaner separation of blacks and whites. And this idea of getting the cleanest separation possible is the idea of maximizing your margin, right? So you see here, what we're doing in SVM is when we're trying to find the optimal line of separation, we're drawing a line and we're trying to use points that are closest to the line and take their distances, right? This is kind of like the margin of separation. So this black point is closest to this red line. So this is its distance, right? And this white point is closest to this line. So this is its distance. And our goal is to maximize this margin distance, right? That way we're giving the most wiggle room and we're also doing the cleanest separation possible with our linear boundary. So a kernel SEM, on the other hand, uses a nonlinear function. So it's the same concept, right? We want to maximize our margin of separation. So that way we're doing a clean separation, right? But instead of using lines as boundaries, we can use complicated functions, which are called kernels, and we can use nonlinear means to do it, right? And find, the maximum margin decision boundary. So let's actually see this in action. So we're going to import SVC support vector classifier. We're going to instantiate our kernel. We're going to use linear for sake of simplicity. You can change this to something called RBF to use nonlinear kernels. So, you can change to RBF to use nonlinear means, but we'll use linear for right now. We're going to instantiate the support vector machine. We're going to fit it on our training set and see how well it does, right? So we'll see here that we get a 78% accuracy on the train set for SVM, while we get a 74% accuracy on the testing accuracy. This is a nonlinear SVM using the RBF kernel. And we see here we do a bit better, right, for our training and testing set. And these are the predictions we get from our SVM on the testing set. So that gives you an intuition as to what the support vector machine is doing. And in the next video, we're going to be visualizing our results and kind of comparing the performance of the models we studied. So till then, see you in the next video.